Okay, there we go. So, good afternoon, everybody. It is a pleasure this afternoon to introduce our guest, Francesca Annibali, from the Observatory of Bologna. Now, it's not anymore Observatory, it's
Astrophysics and Space Science Observatory.
Okay, for me, it's still the Observatory of Bologna, but I'm wrong. So, for those of you who don't know Francesca, many of us already have historical collaborations with her to many different scientific aspects that she's interested in. So Francesca got her degree working with Monica Tosi, something which I didn't know, I just discovered. And then she got her PhD in 2005 with Alessandro Bressan at SISSA. Then she moved on the other side of the pond in the United States Space Telescope since 2005 to 2008 for a postdoc, and then after several fellowships around Bologna, since 2018 she's a permanent researcher at OAS, and since I think 2024 primo ricercatore at INAF. Her key scientific interests quite broadly from galaxy evolution to stellar population, star formation histories, mainly for dwarf galaxies, but not limited to dwarf galaxies. She is part of the Euclid consortium and is actually co-lead of the Milky Way resolved stellar population working group, and she's also deeply involved with Morpheo. She will say something about that too. And today, Francesca is talking about building dwarf galaxies from bottom up, evidence for dwarf-dwarf mergers in the nearby universe. I'll tell you when we have 5 minutes.
Okay, thank you. Thank you for the invitation. It was my first time in town. I'm very happy to be here, see a lot of friends. And so today I would like to talk about this project, which is devoted to understanding how dwarf galaxies build bottom-up, so from the accretion of smaller satellites. And so, before starting, let me put this project into a broader astrophysical context. It's the Lambda cold dark matter cosmology that we know very well, according to which structures should grow hierarchically, following a merger tree, typically represented by this sketch. Basically, that's because the smallest dark matter halos are the first that collapse, and then they start to merge, forming larger and larger structures like galaxies, cluster of galaxies, and so on. And so a consequence of this continuous hierarchical merging process is that present-day galaxies are expected to be surrounded and orbited by a large number of streams and satellites. And indeed, this theoretical scenario is confirmed observationally by the fact that we know today that there is evidence for a large number of satellites and stellar streams around giant galaxies, elliptical, spirals, first of all, around Milky Way. And so here the question is, do we expect similar abundance of structures around dwarf galaxies, otherwise isolated dwarf galaxies? And so, before answering this question, I would like to remind you that a prediction of the Lambda cold dark matter cosmology is that the abundance of substructures within dark matter halos should be scale invariant. So, dark matter is expected to behave in a kind of a fractal way. This is represented by this plot that I will try to explain. Basically, what the authors did here was to compute high-resolution simulations of a Milky Way-like host dark matter halo, where they were able to resolve not only the subpopulation of subhalos, but the second generation of sub-subhalos. And what you see here in this plot is the relative, the distribution, the cumulative distribution of these sub-subhalos as a function of something which is a proxy for the mass normalized to the host subhalo where they reside. And you see in different colors different sub-subhalos, while in black you have the population of subhalos within the large Milky Way dark matter halo. And you see that all these halos behave in a very similar way, striking similar way. This implies that the relative abundance of substructures within other matter halo should be the same whatever mass you are considering. So this is some kind of fractal way, as I was saying, in which dark matter behaves. And so according to this prediction, we would expect that also small galaxies would be surrounded by a lot of even smaller systems. But when we consider, this is for dark matter, when we consider baryons, the situation is much more complicated. And this is because there are many uncertain things that we still don't fully understand. First of all, the stellar mass to halo mass relation that you see here. This is a compilation from different studies. And you see that there is a large scatter of the low mass regime. So this relation is very uncertain at the low end toward the regime of dwarf galaxies. Then the halo occupation fraction is also something that is very uncertain. So how many dark matter halos are going to host a luminous galaxy? And then the threshold for starless dark matter halo also is very uncertain. So what is the threshold below which a dark matter halo will not be able to form stars? So there are very small dark matter halo you don't expect to see luminous galaxies. And also this ingredient is very uncertain. And all these uncertainties in how we treat the baryons translated to large uncertainty for what is the luminous mass that a dwarf galaxy can accrete during its lifetime. And this is well represented, for instance, by this study. This is a study where the authors simulated a dark matter halo for a dwarf galaxy. And they did different assumptions for the stellar mass to halo mass relation. So they assume different models. They also assume different threshold for starless dark matter halo. And then they made predictions for what we expect, what is the fraction of baryonic mass that a dwarf galaxy will accrete during its lifetime. And you see that depending on this assumption, you get very different expectations. So this, just to say that it's very uncertain. This is still very uncertain. And here the importance to get observations in order to better constrain these models. The problem here, however, is that studying dwarf satellites of dwarf galaxies is very challenging because, of course, satellites of satellites are expected to be very faint and difficult to observe. And in fact, as of today, there are very few studies that were able to characterize and identify accretion events around dwarf galaxies. Here I collected just a few examples. One is the famous case of the dwarf galaxy NGC 4449, where a stream was discovered. And so this is a satellite that is accreted and disrupted by the dwarf galaxy. There are other examples of interacting dwarf galaxies. Also, in one case, here there is a kinematic stream that was discovered in a satellite of Andromeda. But other than these examples, which are like sparse and scanty, there are no systematic studies aimed at characterizing the frequency of these kind of events around dwarf galaxies. And that's why we started a few years ago this project. It's called the Smallest Scale of Hierarchy Survey Project. It is a survey done with the Large Binocular Telescope, imaging 45 late-type dwarf galaxies at a distance of less than 11 megaparsec. So our goal was to acquire deep imaging with a large binocular camera, and so we have also a large field of view, in order to characterize the outskirts around this sample of dwarf galaxies and see if they were companions or if these systems had a merging going on. And so this is an overview of the galaxies in our sample. Here are a presentation of the properties. So the sample covers a broad range in luminosity that you see here. we have galaxies about as luminous as twice the Large Magellanic Clouds, down to 1,000 less luminous, so quite range in mass. We selected galaxies with an angular size that could well fit into the field of view of the Large Binocular Camera. This is the distribution in distance, so this is important because you see that large fraction of our system are closer than 4 megaparsec, and this is important because this implies that these systems can be resolved into individual stars from the ground in single limited mode. And then what the bottom right panel shows is the distribution of these systems according to the environment where they reside. This is a parameter that was introduced by Karachentsev and characterized the influence from a massive neighbor. So we have galaxies that are extremely isolated, up to galaxies that reside in groups. Warning is that, of course, we don't have here galaxies that are in a cluster of galaxies, so in very high density environment. And so we exploited the wide field of view and sensitivity of the Large Binocular Camera to image these galaxies and characterize their outskirts. And in order to convince you about the importance of having deep observations, here is an example of one of the galaxies in our sample, as observed by the Sloan. And on the same spatial scale, you see our image acquired with the LBT. You see here that you are able to detect some low surface brightness features that are not visible in the Sloan images. And that's possible because with LBT we really reached very deep surface brightness, about 2930 in magnitude per square arc second. And something that before moving further, I would like also to stress, to highlight, is that we have to be very careful when doing this kind of study, because lake-like dwarf galaxies, like those we have in our sample, are characterized by a very asymmetric distribution and configuration of their star formation. So you have seen probably dwarf galaxies that are forming stars. They all appear like having this irregular distribution of the young stars and so on. And this kind of configuration may easily mimic a tidal disturbance. But in order to identify real disturbances of the gravitational potential, so real merging events in these systems, we have to look at the old stellar component. So that's what we want to do. For this purpose, we will use red giant branch stars that we know are older than 2 gigayears. And so disturbances and asymmetric configuration of this kind of population will tell us that there is a merging or an accretion event going on in this system. And we can indeed play this game very well in our systems because, as I told you, we can resolve, for a large majority of the sample, we can resolve individual stars from the ground in single limited mode. This allows to construct this kind of diagrams, color minus diagrams of resolved stars. Every point is an individual stars. And select from this diagram stars that are in a certain phase, the red giant branch, which traces the old stellar component. And so we go from such kind of diagram to a map of the stars that shows how the stars of different ages are distributed. And so you will see here in red are the red giant branch stars, so the old stellar component. And so we try to look at asymmetries and distortion in this population to identify possible merger events. And so, to make a long story short, out of the total sample of 45 galaxies, we identified 6 galaxies that have very clear signatures of mergers. This you can immediately see just from a visual inspection. These galaxies are here, and you see very well here. You have kind of plumes. Here is an umbrella-like features. You have 2 plumes in the opposite directions. Here is a kind of fan shell, I don't know what to say. And all these features are also traced by the whole red giant branch population. So we know from that these are really indicating that some kind of accretion of merging is going on. And these galaxies indeed also show very peculiar H1 morphologies and distortions in the velocity field of the gas that also testifies that there is something that is disturbing also the gas in these systems. These are just 2 galaxies for an example, but all the 6 galaxies have very peculiar H1 configurations. And for 2 of these galaxies, we ran n-body hydrodynamical simulations. This is the work done by Raffaele Pascale, where it was able to reproduce both the observed configuration of the stars and the properties of the H1. In order to do that, he assumed that a dwarf galaxy that's merging with a smaller system. In particular, in both cases, he found out that in order to reproduce the observable, he needed to have a merger with a 10 times smaller system in dark matter or 150 times less massive in luminous matter. So minor merger between a dwarf and a smaller system. And but now going beyond these 6 systems where we find very obvious evidence for accretion and merging, what we want to do here is to do a systematic characterization of the entire sample, and in order an objective classification. And in order to do that, David Perez Millan, which is a postdoc in Bologna, is introduced this parameter, this new parameter called the azimuthal asymmetry parameter. This is a metric that characterizes the basically considering annuli, elliptical annuli that are centered on the galaxy, is going to characterize, to quantify the variation in the density of red giant branch stars compared to what you expect for a flat uniform distribution. So comparing the observed variation with pure Poisson noise, basically. And so this provides a more objective way of quantifying these asymmetries in our systems. And that's what we obtain for the entire sample. That's the distribution of this parameter. And you see indeed that 4 out of the 6 galaxies with very obvious merging events sits on the high distribution of this parameter. But we have many other systems that we didn't consider from a first visual inspection. What are these systems? For instance, you see some very high values of these AAP parameters. One, for instance, is a system. This galaxy is a famous starbus galaxy, and indeed it was suggested that this galaxy is merging with a smaller system here. And if you look to this color composite image, where red is the H1, you see that the H1 represents a kind of a stream. So indeed, this is a good candidate for merging system. And another system with very high AP parameter is this one. You see of course, the young star formation is very asymmetric, but you see that also the old population presents this kind of asymmetry that we didn't recognize in the beginning. So this approach seems to work very well in identifying additional asymmetries and in this sample. Then something that I would like also to point out is that merger events between dwarf galaxies probably also produce an effect on their star formation history. And this was shown both by observational and theoretical studies. In the top, you see a study by Stewart based on a sample drawn from the Sloan, where the authors showed that there is an enhancement in the star formation in paired dwarfs compared to no paired dwarf galaxies. So meaning that when you have 2 dwarf galaxies that are somehow interacting, you have also an enhancement in their star formation. And also theoretical studies suggest that this is maybe the case. For instance, there are some simulations showing that when 2 dwarfs merge, they trigger some starburst events and produce these massive central cores of young stars. And for instance, this may be a channel for the production of blue compact dwarf galaxies. And also, it has been seen that when a satellite merges with a dwarf, it triggers bars at pericenter passages. And so in order to test this hypothesis, we acquired for 3 galaxies in our sample, 3 of those with clear signatures of merger, we acquired deep HST data in order to derive very deep color magnitude diagrams and be able to infer the star formation histories for this system. So what we want to test is that there are particular epochs where the star formation has been enhanced by pericenter passages of the satellites with the main host. So this is still work in progress. Francesco Ficara, which is a PhD in Salerno, is working on that, and it still has some results about the star formation histories, but I will not show you today his results, but he's working on that. And from this very nice HST data, we also found other interesting results, in particular about massive clusters. This is one of our galaxy, where you see here very well in the LBT image the stream that we identified, and you will see that there is a concentration of stars right here, and this is well resolved in the HST data. You see, what we find here is a very massive cluster. This is as massive as the famous Omega Cen cluster in the Milky Way, which, as you may know, is thought to be the remnant of the nucleus of a remnant of a accreted and disrupted dwarf galaxy. So we are seeing here very similar system in this galaxy, with the difference that here we are talking about a galaxy that has just 10 to the 8 solar massive stars compared to the Milky Way. So it's really striking that we are finding a similar system like Omega Cen in this small dwarf galaxy. And now I would like to move to another object. So DDO68, this is not nominally a system in our SSH sample, but is kind of a pilot project that we started before embarking into this larger survey. So this galaxy is a blue compact dwarf that resides in a very empty region of space. It's in a void at about 13 megaparsec from us. And it's very peculiar because it's one of the most metal-poor star-forming galaxies known. It has a metallicity below 5% solar, so extremely metal-poor, and it's also a strong outlier in the mass-metallicity relation. So its metallicity is way too low, as you can see there, for its mass, its luminosity, but this is also when you compare the mass. And it also presents a very disturbed morphology that you can see here. And for all these reasons, so it has been suggested since the beginning to be, in fact, not just one system, but to be the result of 2 merging systems. So a main body and a satellite, which is responsible for this kind of cometary tail. And in order to get more insights into this system, we acquired deep LBT data again, using the nice LBT. And what we found here was the presence of this additional kind of stream that you can see here. And so at the beginning, we thought this could be a satellite, a second satellite beyond the tail, a second satellite disrupted and accreted by DO68. But of course, we couldn't prove that without a distance. And in order to do that, we acquired HST data, because with HST, we could get very deep CMDs that we could not get with the LBT from a 13 megaparsec distance. And so we really we found that indeed the tip of the Rajayan branch of this small feature, it's the same, is compatible with the distance of the DO68. So these 2 systems indeed appear to be physically associated. It's not just a projection effect. And so this implies that indeed this system has 2 satellites, one that causes the tail and another very small satellite. And that's not the only one, it's not over, because there may be even a 3rd satellite in this system. So in 2014, Cannon et al. Found this small galaxy. They detected it in each one. And this galaxy has the same velocity, systemic velocity of the DO68, and it is just at a projected distance of 40 kiloparsec. So they suggested that this could be a satellite of DDO 68. And the problem with this system is that it was never observed before in the optical because it happens to be completely outshined by a bright foreground star that happens to be on the same line of sight. So what you see here in the gray is not the galaxy, is the bright foreground stars. What we did was to exploit this bright foreground interloper as a guide star for adaptive optics. And so here you see the star, the foreground stars in single limited mode from the ground. That's saturated, that's what you see in the center. And this very diffuse emission is the galaxy behind. What we did with adaptive optics at LBT with Lucy is that. So we were able indeed to resolve the individual stars using the adaptive optics. And I will zoom in order to convince you that really we are able to resolve for the first time the individual stars in these galaxies. And based on this result, we were later successful in acquiring HST data of this system. So what we did was to play this DCS, just a little bit of set from the bright foreground stars, and we were really able to nicely resolve all the stars. You can see here how many stars we are able to resolve in this galaxy. What you see here is the bright spike of the foreground star that still contaminates, of course, our image. And so with this observation, we were eventually able to get a CMD that was deep enough to reach the red giant branch and measure the distance of this system to the tip. And again, this system happens to be at the same distance as DDO 68. So we have, that's amazing, a galaxy that is in a void, but has at least 3 satellites merging on it. A very interesting, I think, system. Let me go to the end of the talk. Let me see what time. Yeah, we have still some time. Just to show you what the perspective that Euclid is opening for this kind of studies. So Euclid has been launched in July 2023. Now it's acquiring data. The first public data release is foreseen for the end of the year. And beyond the main focus of the mission to understand the origin of dark matter and dark energy, Euclid will also allow a lot of legacy science, and in particular a lot of science that concern this kind of merger events and accretion events around galaxies of any kind. This is because of the very wide field of view of Euclid and the high resolution. Consider that the resolution that Euclid has in the high band is just a little worse than that of HST. So it's very high resolution with very large field of view. And in particular, I would like to show you some results that we obtained so far. This is a program, one of the early release observation programs, targeting 3 dwarf galaxies and 3 spiral galaxies that you see here. So what we did from this data was to construct very high quality color magnitude diagrams. You see here an example, from which again we can play the same kind of game that I've been showing during all my presentation. So identify stars in different evolutionary phases through these CMDs, and then analyze their distribution, their spatial distribution. And since the Euclid field of view is very large, we can do that for the entire galaxy. Also, what typically cannot be done with the smaller field of view instrumentation. And so we were really able to study the outskirts of all these systems, as shown here. And also something that I would like to highlight is a kind of warning when you are trying to study features in the outskirts of galaxies using integrated light versus count. So as an example here, this is one of the galaxies that was imaged by Euclid. It's a spiral galaxy. And you see the this is the image in the vis channel, so in the high band. You have in cyan overplotted the contours for the H1 emission. In purple, you have the far infrared emission. And what immediately caught our attention was this kind of stream feature that you can see here to our top right. So we were wondering if this could be some kind of stream or satellites or whatever. So we analyzed the distribution of stars that we resolved in our Euclid image. This is the distribution of young stars that nicely trace the spiral structure. This is the distribution of intermediate age AGB stars. That's the distribution of all stars. And you will see that there is no counterpart in the stars, the stellar component, about this feature. Any idea of what this feature can be? Any suggestion? So in the end, what this demonstrates and what we think is that this feature is just cirrus from our own galaxy. So something that you would have interpreted as belonging to the galaxy itself is indeed only foreground emission. So we have to be very careful when we try to interpret integrated light studies, because that may be very misleading. And this, on the other hand, result stars will tell us what indeed is something associated to the galaxy, what is stellar population associated to the galaxy and what is not. Well, and here is a study also that we did, still exploiting these beautiful early release observation data about one of the dwarf. This is IC10 at a distance of 1.7 megaparsec from us. Very nice CMD, allowed us to explore. So you see on the same scale what is the image, the light that you see, what is the distribution of stars, the red giant branch stars. So you see that you are able to really trace the extension of this galaxy to much to further out than possible just looking at the light, at the images. And what we see here is that the distribution of the old stars is asymmetric. It has an elongation that very interestingly match the direction of a gaseous satellite that was previously identified. Unfortunately, the field of view of Euclid doesn't go up to the gaseous satellite, but what we are seeing here is just an hint of the effect of this merging event. Or otherwise, it's also possible that what we are seeing is the tidal interaction with Andromeda, because very interestingly, the elongation that we see in the red giant branch stars is in the same direction of the motion of this galaxy compared to Andromeda. So both possibilities remain open at this point. And we'll not go into the details, but basically we were able to trace the profile, the stellar profile of this galaxy out to very large radii. And what you find is that there is an excess in the outer region compared to a pure Cercic profile. And this is maybe it's meaningful at the light of prediction from simulations. These are simulations where the authors show the distribution of in situ stellar components, so what formed in the galaxy and what was accreted. You see, so the in situ is what you have in orange, and the ex situ mass, what has been accreted during the galaxy lifetime, is what you see in blue. And so you see that the ex situ material typically dominates a very large radii. So we need to go very out, so very farther away from the galaxy in order to be able to detect whatever material has been accreted from satellites. And so, future perspective, of course, as I said, Euclid is opening really bright future for this kind of study. This is the footprint of the Euclid Wide Survey in yellow, and you see that Euclid will image many dwarf satellites of the Milky Way. It will also sample many late-type dwarfs in the local group, and then many galaxies in galaxy groups like M81 and so on. And so really, this will be amazing. We'll be able to trace these galaxies out to large radii, study the stellar component in great detail. And then still talking about future perspective, if Euclid will, with this large field of view, will allow to study the outskirts of many galaxies, we will need a very high resolution in order to study systems like that. So remnants of nuclei of accreted system, like the one that we detected in NGC 5238. So as you know, so ELT will of course play a fundamental role in this kind of studies. As you know, INAF is deeply involved into a project, Morpheo, which is the adaptive optics system for DLT. In the beginning, it will feed Mikado, which is the near-infrared high resolution camera for DLT. It's also the first light instrument. And later, after some years, it will also be coupled with Harmony, which is the IFU. This incredible resolution allowed by this instrumentation plus the correction for of adaptive optics will allow to target a broad range of scientific cases from the solar system, exoplanets, the results of the population, redshift, and so on. And so in the science team now we are working on the revision of the white book, the first white book that was done by Fiorentino et al. In 2017. So this revision is necessary both because of the revision of the performances of the instrument and because of new, of course, discoveries, with more recent year, most important one, of course, from JWST. So we need to account for many other important science cases that were not considered in the beginning. And so, of course, this to say that, of course, we would be happy to have input from the community about interesting science cases that can be done with this high resolution. And so if you are interested in participating to the white book or you want to contribute with some ideas, you're of course welcome to, you can either contact me or contact Michele, which is also involved in the project, or Elisa Portaluri, which is connected online. And that's all. Thank you.
Perfect. Thank you, Francesca. Questions?
The curiosity. I understood that the main tool that you use to trace the possibility of this interaction between different dwarfs is the asymmetry in the distribution of the whole. But this tool indeed is valid only if the galaxies are, let me say, almost in isolation. Because if it is as in the, for instance, in the local group, by dwarf is cannot be used.
You can use it, but you will detect asymmetries due to interaction from a more massive.
So you cannot discriminate.
No, you cannot discriminate. So something that I have to say is that typically for the kind of sample that we selected, which are late type dwarf galaxies, because of the morphology density relation, these are also typically isolated systems. So of course, they're not much affected by a massive companion like Andromeda or the Milky Way. And so we don't have this kind of bias, let's say, because our systems are relatively isolated. I agree with you that, like in the case of IC10, we see a distortion in the stars. We cannot tell if it is, at least with the data in S, we cannot tell if this is tidal effect from a more massive host or accretion of a smaller system. Maybe studying we are trying to do that, studying the metallicity distribution, the spatial distribution of metallicity within the galaxy using colors, for instance, may tell us something, because you would expect the features generated by an accreted smaller system to be more metal poor because of the mass metallicity relation, but this is not easy to do with photography. So.
I'm sure. No. Legal question. H5 initial is.
Sorry, H1. Neutral hydrogen. H1, yes. 21 centimeter.
Okay, okay. So the question is, those are
Radio observation.
data.
Yeah.
So
Yeah.
is there possible evidence of strings between these galaxies?
Yes.
Radio wavelengths are not visible.
Yes. For all the sample of the SSH sample, there are archival H1 data that we are going to analyze. Many of these galaxies show very disturbed morphologies that may be due in fact to the merger. It's not that obvious because sometimes you have many cases where the H1 is very much disturbed, but the stellar counterpart is not. So it's not having a disturbed H1 is not necessarily an indication of merger, but of course we see that in the case where the stellar component is disturbed, also the H1 is disturbed.
It just a diffuse gas, not integrating due to gravitational perturbations. Yes, okay.
Yeah, for some reason, yeah, right.
Thank you.
Okay. Other questions? I don't mind second. Okay.
Yeah. Go.
No, so more. So, Euclid, how much can you do what you've done with Euclid for the SSH survey? I mean, because it's a massive work, first of all, but then it also has some specific needs in terms of depth of resolution. So, do you expect to do the same?
You expect to do better.
Yeah, but for.
And
then the other question is machine learning.
Okay, so we expect to do better. Actually, you know that we are already working on the year 1 data within the consortium, and I'm already working on the galaxies of the SSH sample that have been observed by Euclid. And you can do that much better because the resolution of Euclid is much better than what we have from the ground in single limited mode. So you are able to get much better photometry of point sources and to get much deeper CMD, so to get better characterization of these low surface brightness outskirts. And of course, still with Euclid, you can do this up to some megaparsec distance. So it's not something you can do in the very distant universe with this kind of approach. So in this sense, machine learning probably is not going to make a tremendous improvement for this kind of study because the sample is not enormous. It's huge, but not huge. No, it's still under 100 of objects, I would say. So still something that can be done in principle. That doesn't really require, but of course, other studies that involve distant galaxies, more distant galaxies. We are now working on some identification of dwarf systems that are not that. Of course, this must be built on machine learning because the volume would be too big.
So Virgo is not covered by Euclid.
No, it's not covered. This is 18 megaparsec. At 18, you cannot. You don't have enough resolution with Euclid to.
So you really need to resolve single stars.
You cannot resolve single because the resolution in this is good. It's 0.15 arc second, but in the mist band it's 0.4, 0.45. It's much better. So it's going to kill you at 18 megaparsec distance. That resolution. No, but for galaxies up to 4 or 5 megaparsec, it's perfect. I mean, you can still. Of course, not the central part of galaxies, but the outskirts can be nicely resolved with that resolution.
So, and you really need to resolve that because otherwise there's Fornax.
If you want to do this kind of approach, yes.
Fornax
is
20 megaparsec.
Yeah, still like Virgo. You can go in groups, M81 groups.
So you cannot do the same thing. I mean, kind of analysis without resolving stars, but doing integrated flow.
It's a different kind of. Yeah, you can identify streams in the, but
Yeah.
I said with the limitation of the integrated light. Yeah.
Other questions, Francesca? If not, then grazie Francesca.
Thank you.
Let's leave it here and stop recording. Okay.
Quindi se volete, if you're interested in the science that we